Okay, so we're going to start by talking about the properties of acids and bases. So we're going to look at each following statement and determine if it describes an acid, a base, or both. So here, starting with option A, produces OH negative ions in water. So OH negative is a base, and that just comes through either memorization from lecture or the book. And then we also know that the proton is H+, so by process of elimination, we know this is a base. And so then moving on to B, conducts an electrical current in the solution. So that would apply to both an acid and a base. So we'll put both here. Okay. And then moving on to C, has a slippery feel. So that would apply only to a base. And lastly is turns litmus red. Now, it's red, that tells us by, when we see red there, we know that that applies to an acid only. If this were to say blue, that would be applying to a base. So as you can see, most of these options A through D, this really comes as a means of memorization, either through lecture or the book, in order to be able to answer these questions. Okay? So now we're going to move on to naming acids and bases. So we'll start with A. So in this case, we're given the name, calcium hydroxide. So these ones are pretty straightforward. So we got calcium, and then we got hydroxide. And we know that calcium has a +2 charge. So then hydroxide, which has a negative charge, we're going to need 2 of those to balance it out. So we have calcium and hydroxide 2, and we put those in parentheses. And then moving on to option B, we have HI. So anytime we see one where it just has an H and it's followed by a non-metal, we know that we can just, it's going to start with hydro, and in this case it's going to be the iodic. We're just going to do the base, and then it's going to end with acid. So that's going to be there anytime we see just, the H alone with the non-metal. So here we have sulfuric acid. Sulfuric acid. And this just really comes through memorization. There's that trick you can use that he mentioned, where he says, I ate something icky. Something icky at the White House. So in this case, the sulfate will be replaced with the IC, and in this case, it would be the ite and aus. So that's a memorization tool you can use. With time, I think you're just going to be able to memorize that it's, when you recognize this, it's sulfuric acid. As you remember, the polyatomic on its own is, SO3, and that has a charge of 2, a -2 charge. So that's why we need 2 hydrogens to neutralize it. So while this memorization tool is given, I just found, just writing it out a couple of times and memorizing it on your own that way. I wasn't a super big fan of this one, but some people may like it, so I wanted to give it to you. The next one here for D is sodium hydroxide. And this one's pretty straightforward. We have negative with the OH, and then -1, and then a +1 with the sodium. So we can leave that alone. Okay, and then moving on to option E. So this is really similar to B, where we have, you see the hydrochloric and then acid. So the hydro is going to be the H, and then you have the base there of the chloric, so we know that's the Cl. So hydrochloric acid. And in this case, you know, there's no additional subscripts that are needed. So the nitric acid F, moving on to F, is very similar to C, where you only see the, although you don't see the hydro, it's still there. So for nitric acid, it's going to be H and O subscript B3. Okay, and that's how we name the acids and bases. So for this set of problems, we're going to be trying to identify the acid and the conjugate base, along with the base and the conjugate acid. And so what I like to do is definitely look at both sides of the equation to help you figure out which one's the acid and which one's the base, especially in cases like this where, you know, you see a hydrogen on both sides. So you have to look at the other side to really see what's happening with the hydrogen. So for example, here we have the HCO3, and on the other side we see that the H is gone along with the positive charge. So here we have HCO3 with a negative charge, and here we have the CO3 with a -2 charge. So it lost not only the H, but also the positive charge, which is indicative of an acid and a conjugate base. So here we have the acid and the conjugate base. So then by default, that makes this the base, but let's go ahead and look at that. Here we have H2O, and on this side we have H3O plus. And so that means here we gained not only hydrogen, but a positive charge, which is what we're looking for. So that makes it an acid. So that would make this the base, and this would be the conjugate acid. Okay. So we'll go ahead and do the same with the next one. So we have HCO3 with a negative charge, and then we have HCl. So again, you know, we have hydrogens on both sides, and we don't really know if anything's being given, you know, donated or received until we look on the other side of the equation. And so for the HCO3 with a negative charge, we now see an H2CO3. So it looks like it gained a hydrogen along with a positive charge. Versus here under the HCl, it looks like we lost a hydrogen along with the positive charge. So in this case, the HCl would be the acid, right? Because that's the one that donated the H plus, and the Cl negative would be the conjugate base. And here on this side, the HCO3 negative is actually the base. And here on this side, we can see that it's the conjugate acid. So these two are connected, and these two are connected. Okay, that takes care of these types of problems. So in this next problem, we're going to get more practice with the acids and writing in the conjugate base along with the base and conjugate acid. Now this can look a little intimidating at first, but if you just, I noticed if I just, stayed on one side, looked at the acid and the conjugate base, first before moving on to the base and conjugate acid, it made it a little easier. And this is actually really good practice. So with this H2O, we know this conjugate base, we know this acid wants to donate, we know that the conjugate base has to have an H plus less than the acid, because the acid needs to be able to donate that. So an H2O without the additional, H plus is going to be OH negative. So you can see how OH negative, you add an H plus and it becomes H2O. So we're going to use that very same logic here with the conjugate acid. So it needs to donate, the conjugate acid has an H plus to donate. So in order for us to get the base, it's going to be without the H, so you're going to see an S. But we also have to address the charge, because we know that the acid is donating an H plus, not just the H. So that's where instead of just having a negative charge, we're going to have a 2 negative charge. Okay. So now going back to, in this case, we have the conjugate base and we need the acid. So this acid needs to be able to donate an H plus. So we're going to have an H, SO4. But we can't forget that the charge is there. So actually this SO4 should have a 2. So when it donates the H plus, it reduces because it now has a positive charge. So now it's an HSO4. So moving on to this side where we're looking at the conjugate acid. And so now that the base has to be able to receive an H plus, so that would look like an NH3. So it's able to receive an H and a positive charge, and that's when you would see how it relates to the conjugate acid. So now let's go back to an acid here. So it's NO2, because we know that it doesn't have the H, but it also is impacting the charge. So this is going to be an NO2 negative. And then moving on to the base here, where we know this is the conjugate acid has an additional H plus, so it's going to be H, and instead of 2 it's 3, because there's an additional 1 there, O, and then you're also going to have the positive charge. Okay, so I think you're going to be seeing a pattern at this point. So the last one that we're going to do here is we have the conjugate base, and we know the acid has to be able to give an H plus. So here it has an H2, but our acid's going to need H3, PO4, and that makes it neutral, because that positive and that negative will make it neutral. So there's a neutral charge there. And for the conjugate acid, you're going to see here's the base, but the acid needs to be able to give an H plus. So we have H, PO4, and then it only has a negative charge of 2. And that's how we are able to fill in the acids and the conjugate bases, along with the bases and the conjugate acids. So lastly, we're going to go over Le Chatelier's principle to predict whether the following changes causes the system to shift in the direction of the products or the reactants. So here we have a hypothetical equation here with A plus B, and then on the reactant side, and then C plus D on the product side. So if we add more A, to the solution here, the principle says it's going to shift on over to the right. So if we add more A, it's going to shift over to the right and try to create more products to maintain a equilibrium. So here we'll go ahead and put, it's going to shift right. And consequently, same thing here. If we add more B, then it's going to again shift right to create more products to maintain equilibrium. So here we'll go ahead and put shift right. And then if option C is if we add more D, then we're going to go ahead, the system is going to shift left to try to create more reactants to maintain equilibrium. So in this case, it's going to shift left. Now here's a slightly different scenario. We're going to remove A. So if we go ahead and remove A, then there's going to be a shift to the left because it's going to want to create more reactants in order to maintain an equilibrium here. So here we're going to say that it's going to shift left. And lastly here is if we move some on the product side, in this case C, it's going to want to create more of C in order to maintain an equilibrium here. So in this case, we're going to say shift right. Okay, and that does it for that principle.